In this clip, we'll be analyzing a velocity versus time graph. So these are typical questions that we see for this kind of problem. I encourage you to hit pause, try the problem on your own, and then come back once you did so that we can look at the solution together. Alright, let's look at A. So part A, at what time is the train changing direction? So here we have a velocity versus time graph. And you can see that the velocity is initially positive, but then it becomes negative for a little while before becoming positive as well. When you look at the velocity versus time graph, every time you have a change in direction of the object, this corresponds to a moment where the velocity will change sign. So in this situation, we have change in direction of the object at 1 second and at 6 seconds. And this can be seen easily on the graph by identifying the points where the velocity changed sign. B, during which interval is the train speeding up? Speeding up is fairly easy to identify. We just want to look for when the velocity was 0, and then the magnitude of the velocity has to be increasing. So every time we're going away from the 0 axis, we are dealing with a case where it is speeding up. So in here in blue are the two intervals where the object is actually speeding up. So again, speeding up, the curve is going away from the 0 axis, and by opposition, slowing down would be when the curve is going toward the 0 axis. So in here, the speeding up is happening in the interval 1 to 2 seconds, and also in the interval 6 to 10 seconds. Then part C. What are the speed and velocity at 1 and 4 seconds? Well, this is a velocity graph. So to find the velocity, you just have simply to read the graph. So that should be fairly easy. For the speed, remember that speed is always positive. So this means that we will take the velocity and just take the absolute value. So in here, at t is equal to 1 second, we will have for the velocity Vx, we just look, and in here you see that it's 0 meters per second. We are looking at this point here, and the speed at that moment is also equal to 0 meters per second. Okay, and finally at t is equal to 4 seconds, we are at this point in here, so you can see that the velocity will be equal to -2 meters per second, but the speed will be equal to +2 meters per second. Alright, so I remind you that when there is the subscript x, we're referring to the velocity. Without subscript, that's the speed. Next, part D, what is the acceleration at t is equal to 1 second and t is equal to 4 seconds? Acceleration, by definition, is just equal to the change in velocity over the change in time. So what we want to do is just to make that calculation. So at t is equal to 1 second, we can pick 2 points. I'll switch color to, let's say, green, or that's a bad choice, let's say red. So at 1 second, I can pick this point and this point, let's say. And what I will do is just to find the actual, or use the actual definition. So change in velocity over change in time. So I take the velocity at 1 second, which is 0 meters per second, minus the velocity initially, which was 4 meters per second. I divide by the time interval, 1 second minus 0 second. So we end up with -4 meters per second square. Sign makes sense because the slope is negative, so we expect a negative sign in here. And then if we do the same thing for t is equal to 4 seconds, same definition. So we start with the change in velocity over the change in time. But this time we have to select new points. So around 4 seconds, I could take this point, let's say, and this point. So when I plug the values in, the velocity at 6 seconds will just be equal to 0 meters per second. The velocity at 4 seconds is -2, so -2 meters per second. I divide by the difference in time, so that's 6 seconds minus 4 seconds. And you can see that this time we'll have a plus sign because we have 2 negative. So we'll get +2 meters per second divided by 2 seconds. So this will give us +1 meters per second square. Again, positive this time makes sense because the slope is indeed positive. So part E, what is the displacement between 0 and 10 seconds? since we have a velocity versus time graph, to find the displacement, we have to look for the area under the curve. As we discussed previously, when you find the area, you have always to use three boundaries if you want. There's the curve itself. The second boundary, it's that all areas have to touch the 0 axis that we have here horizontally, and then we're allowed to have vertical lines as well if needed. So in the end, we have three areas in here. One in here that is on the positive side, and that we'll call A1. A second triangle here at the bottom that we'll call A2. And finally, a third triangle in here that we will call A3. So when I calculate the area, I want to consider them as being positive all the time. Even when they are on the negative side, it makes things a little bit simpler. So for A1, the absolute value of area A1 will just be equal to the height, so 4 meters per second, times the width, which is 1 second. And because we're dealing with a triangle, I have to divide by 2, which will give me an area of 2 meters. I can do the same thing for A2. And A2, the height is now minus 4 meters per second. But anyway, I want to take the absolute value, so I won't care about that. The time interval that we have to use, which is the base of the triangle, will be 5 seconds. And again, because it's a triangle, I want to divide by 2. So this means I have 10 meters in here as the displacement or the area for 2. And we do the same thing for area number 3. And for area number 3, again, the height is 4 meters per second. The width this time is for 6 seconds from 6 seconds to 10 seconds. So that will be 4 seconds divided by 2 because it's a triangle. And we get 8 meters. So once we have these areas, the only thing left to do to find the displacement is to add the areas that are on the positive side of the velocity and subtract the area that are associated to negative velocities. So in here we would add A1 and A3, but we want to subtract A2. So in the end, once we plug the numbers in, we have 2 meters minus 10 meters plus 8 meters, the area 3, which gives us a grand total of 0 meters, which means that the displacement of the car, or the train, I'm sorry, over these 10 seconds is just equal to 0 meters. If what we want instead is the distance, we are dealing with the same areas. The only difference is that we want to add all the areas together, because even if it's moving backward, we still want to add that quantity in there. So in the end, the big difference is that we will have 2 meters plus 10 meters plus 8 meters for a total of 20 meters. And that's the distance covered during the 10 seconds. Next, we want to find the average speed and average velocity during the 10 seconds. There's no easy trick for that. The best way is to go back to the definition. So average velocity, or let's start with average speed. Average speed we know is the total distance covered divided by the time interval. So in here the distance is just 20 meters divided by 10 seconds, so we get 2 meters per second. And if we want to do the average velocity, it's the same idea, but we want to use the displacement instead, which was 0 meter in here. So we get an average velocity of 0 meters per second. Lastly, we want to sketch the corresponding acceleration and position versus time graph. So let's start with acceleration, since that's the easiest of the two. So if we have the acceleration here in meters per second square, just as before, I won't worry that much about numerical values. It's mostly the shape of the graph that is important to me at this stage. So at first, you see that the velocity has a negative but constant slope. So we know that we should expect an acceleration that will be constant but negative. And you see that it's fairly steep. So let me draw it like that. And then starting from 2 seconds on to 10 seconds, it's the same slope all along. So the acceleration is constant, but this time the acceleration is also positive and not quite as steep. So let's say something like that. In between, as we discussed previously, there's not really a vertical line, but when we look at it on the graph, we can draw it vertical. In real life, it is a bit smoother and then it curves a little bit at the edges there. Okay, but like this, that's fine. Then we can move on to the position versus time graph. And the position versus time graph, now we'll have position in here, so x in meters. And remember, to do this one, we want to think backward. So what does thinking backward means? It means that at first, you see that your velocity is positive and quite large. So we know that the slope at the beginning needs to be positive and quite large. Then the slope will reach a value of 0 when the velocity gets to 0. So we know it will be flat. And then at 2 seconds, the slope is now negative and quite large as well. So we'll have something like this. And this portion corresponds to one single parabola because the acceleration is constant over that region. So to draw the curve, it will start like that, curve up, and then come back down. So that's the first section that we have. Then at 6 seconds, we know that once again it needs to be flat. And at 10 seconds, the slope will be back to be positive and roughly the same as it was initially. So something like this. So once again, what I want to do is to draw a parabola because we have a constant acceleration in here. So we know it's a single parabola. And the parabola will go down, will hit the minimum at around 6, and then we'll come back up. And just as we expect, the displacement should be 0, so it starts and it ends at the same point. By the way, I decided to start at x equals 0. There's nothing in the problem that tells me to do this, but we can make this assumption if we want to. It's an arbitrary choice. So you see in here we have a collection of two parabola that are joined together at t is equal to 2 seconds. And that wraps up for this problem, which was analyzing a velocity versus time graph. So I'm expecting you to be able to do all that was covered in this clip.